According to a study of U.S. homes that use heating equipment, the mean indoor temperature at night during winter is 68.3 degrees Fahrenheit. You think this information is incorrect. Okay, so that's the key sentence. You randomly select 25 U.S. homes that use heating equipment in the winter and find that the mean indoor temperature at night is 67.2 degrees Fahrenheit. From past studies, the population standard deviation is known to be 3.5 degrees Fahrenheit, and the population is normally distributed. Is there enough evidence to support your claim at alpha equals 0.05? Use a p-value. Okay, so if we articulate the hypothesis statements, we would have the null hypothesis as mu is equal to 68.3, and the alternative hypothesis as mu is not equal to 68.3, because they say it is 68.3, but you think this information is correct. And then at the bottom, it says, is there enough evidence to support your claim? Your claim is that this information is incorrect. That means the claim is the alternative hypothesis. That is the claim. So we went through last week and we did the calculations, and we'll do that again. I'll do it on the TI today. And that was the z-test. So stat test, z-test, and I've already got the information in here, but 68.3 was our population mean that we were comparing against. The standard deviation was 3.5. The mean was 67.2, and the n was equal to 25. And I made sure that I'm highlighting this not equal to at the bottom, and your calculator might look a little bit different from mine. But the keystrokes are the same. Okay. And then I'll hit enter. I've got my p-value of 0.116 and my z-statistic as negative 1.57. Well, what does that mean? The p-value is greater than the significance level, which means the p-value is greater than the significance level because it's 0.05, and our p-value is 0.116, which is greater than 0.05. So that means we failed to reject the null hypothesis. Well, if you grab your decision rule that we talked about before, and our claim was the alternative hypothesis, and we failed to reject, so that means there is not enough evidence to support the claim that you think this information is incorrect, that the mean indoor temperature is 68.3. Did we do it here? Here we go. Let's go to, skip to the end. There you go. There's not enough evidence at the 5% level of significance to support the claim that the mean indoor temperature at night during winter is different from 68.3 degrees Fahrenheit for U.S. homes that use heating equipment. And so I just wanted to take some time to articulate that problem, because I remember when I went through the recording, I didn't hear where we said what the null and alternative hypothesis was. We just kind of skipped to the solution or the conclusion. And so that is from last week. And now we're going to skip over to this week, where we're talking about confidence intervals is where we're going to start, where the standard deviation of the population is not known. And this section should go fairly quickly. And we start off with a conversation about the t-distribution. When the confidence level, the population standard deviation is not known, we use something called the t-distribution. And the sample size is less than 30, and the random variable is approximately normally distributed, we follow a t-distribution. So t is then equal to, and this is going to look similar to the z. So z was x bar minus mu over this population standard deviation over the square root of n. This time, instead of using the population standard deviation, we're going to use the sample standard deviation. Okay, that's the difference between the t and the z. And there's also another subtle difference there as well that we'll get into in a second. Critical values of t are denoted by t with the subscript of c. All right, what are some of the properties of the t-distribution? Well, the mean, median, and mode are equal to 0. It's approximately bell-shaped and symmetric about the mean. The total area under the curve, again, is 1. The tails in the t-distribution are a little bit thicker than those in the z-distribution. And the z-distribution is the standard normal distribution. And then the standard deviation of the t-distribution will vary with the sample size, but it's greater than 1. Okay, let's get to the picture. So the t-distribution is a family of curves, each determined by a parameter called the degrees of freedom. The degrees of freedom is another place where the t is going to differ from the z. We're going to use degrees of freedom, which is n minus 1, or the sample size minus 1. And then the degrees of freedom are the number of free choices left after a sample statistic such as x bar is calculated. And then here is what I just told you, n minus 1. The degrees of freedom are equal to 1 less than the sample size, so n minus 1. And that's a little about the t, and we'll see how we use these as we progress forward. Notice we got in the blue, there's a standard normal curve. But if you have degrees of freedom of 5, notice how the n gets a little bit thicker, and degrees of freedom of 2, the n gets a little bit thicker as well, in addition to what it was at the degrees of freedom of 5. For 30 or more degrees of freedom, the t-distribution is close to the standard normal distribution. Okay, find the critical value for a 95% confidence when the sample size is 15. Okay, how do we do that? Well, we have to contend with the degrees of freedom. And the first way that I'll mention how we do this is to look at a table. So notice in our table, I've got a sample size of 15. My degrees of freedom are n minus 1, which is 14. So I'm looking here at this 14 df, degrees of freedom, 14. And I'm at a 95% confidence interval. At the top, you see the level of confidence, 0.95, and then I just read across and down, and I see I'm at 2.145 as my critical value. Okay. So with technology, let me show you what that looks like in a graph, just so you can tell. It's 2.145 and negative 2.145, and that's going to become important here in a minute. And then when you use technology or the TI 84 plus, we'll start with that one. You want to use inverse T, and they're kind of giving you an idea of how to use inverse T here. Notice if I'm at a 0.95, level of confidence, I usually do it like this. 1 minus 0.95 is 0.05. And then I divide that by 2, because that's going to give me my area in both sides. So here I have 0.025, and here I have 0.025. Well, this 975 is coming from, they're taking this whole 95 and they're adding to it 0.025, which is here. So this 0.025 plus the 95%, and they get the 0.975. That's how they get that number. So then you do inverse T. So let's look at the calculator here. So second VARS, inverse T, which is option 4, 0.975, and 14, which was my degrees of freedom. And you get the 2.145. So to find your T critical in the TI-84, you're going to use inverse T from the VARS menu, second VARS, which is the distribution window. Okay. Now in StatCrunch, stat calculators T, I'm going to enter in my degrees of freedom, 14. I'm actually going to go to the between calculator as well. And then 0.95. And I get my 2 critical values where my cutoff points are. And that's negative 2.145 and 2.145. In the homework, they're going to be asking you for the positive 2.145. And that's how you find the T critical values. And we'll do that again because we'll need to find it in some of the examples we'll do here in a minute. All right. So let's figure out how we're going to work these problems. You randomly select 16 coffee shops and measure the temperature of coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit. With the sample standard deviation, this is how you know between Z and the T, sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. So what do I want to do? First off, where's all my information? You've got X bar here. There's your X bar, 95% confidence. 10 degrees Fahrenheit is your sample standard deviation. And then we're going to find the T critical value. And since we're practicing this, the T critical was at 0.95. So 0.975 and 15 was my degrees of freedom. So I'm at 2.131. So inverse T, second VARS, if you didn't catch that from before, option 4, 0.975 and 15, my degrees of freedom. So we get a T critical value of 2.131, and you can find that in the table as well. Like they're giving you table 5, you can find that there. And so the margin of error for the T distribution is the T critical times the sample standard deviation divided by the square root of n. So that means 2.131 times 10 divided by the square root of 16. (2.131 times 10 divided by the square root of 16, the square root of n. I love it when it does that to me. So about 5.3. So if your calculator ever gives you the fraction, just math, and then 2 for decimal. Oh, calculator's not on screen. Math, and then 2 for decimal, and it takes you to the decimal of the answer that you just got in fraction. Okay, so now we'll define our left endpoint and our right endpoint. Remember that the mean was 162, and the standard deviation, the margin of error, excuse me, was 5.3. So remember, we're going to subtract and add from our margin of error with our margin of error from the mean. So for the left endpoint, we get 156.7, and for the right endpoint, we get 167.3. What does this mean? We are 95% confident that the mean temperature of coffee sold is between 156.7 and 167.3. So let's go back and look at how we would affect the confidence interval with technology. So I'll start with the calculator since I've got it up here, and then we'll move to StatCrunch. You can use either one on the exam. So all right. Stat tests, and we're going to go to T interval, and that is option 8. Then you're going to put in your information from the problem. X bar is 162. The standard deviation was 10. N, in this case, was 16. And my level of confidence was 0.95. So that gives me the lower of 156.67 and the upper of 167.38. Sorry, I can't make this much bigger than that. Oh, maybe I can a little bit. There we go. So that's how it is on the calculator. On StatCrunch, we're going to go stat, T-stats, one sample with summary, and then put in the sample mean. We had 162, sample standard deviation was 10, the sample size was 16. Confidence interval, and we did at the 0.95. I like to show the critical value and compute. Here is your lower and upper limit. Sorry. So what I want you to do is think about kind of all the information that we have in the problem. That's going to be the first part. So we have 36 cars. This is my N. Sample mean is 9.75. Sample standard deviation, sample, that tells me I'm using T, is 2.39, and we're constructing a 99% confidence interval. So first of all, let's find our T critical value. And again, you can use table 5, or you can use the calculator, or you can use StatCrunch. So I'll just kind of float back and forth between the calculators here that were the devices we're using, and we'll just do StatCrunch for this one. So stat, calculators T, go between. Degrees of freedom, our N was 36, so our degrees of freedom is 35, and we're at a 99% confidence interval. So I'll put 0.99. So my T critical value is 2.7238. So that's important information. Remember, my margin of error is T critical times the sample standard deviation divided by the square root of N. So in this case, it was I'll lop that off, 2.724 times 2.39 over the square root of 36. That's going to give us about 1.09. And what do we do with this information? Well, we're just going to add and subtract it from the mean. So we got 9.75 minus 1.09, and then 9.75 plus 1.09. So 9.75 minus 1.09 is 8.66. And then 9.75 10.84. 9.75 plus 1.09 is 10.84. So what does that mean? That means we are 99% confident that the true mean is between 8.66 and 10.84. And let's put the wording in there with it. The true mean, we can say that the population mean number of days the car model sits on the dealership's lot is between 8.66 and 10.84. Okay. Now, we want to distinguish between when we use the T and when we use the normal distribution, or the Z. First, we ask ourselves, is the population normally distributed, or is n greater than or equal to 30? If the answer is yes, then we ask ourselves, is the standard deviation of the population known? Remember, this symbol is the population standard deviation. S is the sample standard deviation. Okay. So if the population standard deviation is known, then we're going to use the standard normal distribution, and that is with the Z critical value. So we found that in the calculator using inverse norm, and in StatCrunch, we used Stat Calculator's normal. Okay, it's not wanting me to put it up there. That's how we found the Z critical value. In the T distribution, if the population standard deviation is not known, the T critical, we use inverse T in the calculator, or in StatCrunch, we use Stat Calculators and T. Okay. So we're going to look at a scenario. I'll let you read it. I'll give you a few minutes to read it. And we're going to decide, are we going to use the T distribution, the normal distribution, or neither? So take a minute or so to read through it. Overwhelming answer is normal. So is the population normally distributed, or is n greater than or equal to 30? So they told us it was normally distributed. And this is the question that Avery was asking. Note that even though n is equal to 25, it's less than 30, you can still use either the standard normal or the T distribution because the population is normally distributed. Is the population standard deviation known? Yes. So yes, we're going to use the standard normal distribution. Okay. Any questions on that?
No, ma'am.
That is how we find the confidence interval using the t-distribution this time. And I think you're pretty good about looking at, do you have the population standard deviation? Do you have the sample standard deviation? That's how you'll determine between the two. Okay. Let's look at hypothesis testing then. With the standard deviation of the population unknown. Okay. So hypothesis testing for the mean where the standard deviation is unknown. We're going to find critical values again. We're going to see how to use the t-test to test whether the population mean, to test a mean when the population standard deviation is not known. And then we're going to use p-values again. So the same rules apply with the p-values. We'll find the critical value in a t distribution, but we just did that, right? We use inverse in our calculator. We use inverse t, right? To find the critical values. But here are the steps again. Specify the significance level. Identify the degrees of freedom. And so you can use table 5. If the hypothesis test is left-tailed, you use a one-tailed column with a negative sign. Right-tailed, you use a positive sign. And a two-tailed is a negative and a positive sign. So let's look at what that looks like on a graph. So left-tailed test, of course, the rejection region is on the left. A right-tailed test, the rejection region is on the right. And on a two-tailed test, the rejection region is in the tails of the distributions. Now, we want to find the critical value for a right-tailed test given alpha equals 0.01. So what is or are the degrees of freedom in this case? What are the degrees of freedom?
16.
16, because we got n minus 1. Okay. All right, and then we can use table 5. In the calculator, because this is a right-tailed test, we still go to inverse t, but this is a right-tailed test. So I'm going to put 0.99, and the degrees of freedom correctly this time is 16. Enter, so 2.58. And I said I was going to float back and forth, but degrees of freedom 16. 99. 01. Because in StatCrunch, because you're changing this sign over to it saying this is right, a right-tailed test, you can put 0.01 there. So that's the difference between the calculator and StatCrunch. In StatCrunch, you can put 0.1 as long as you select this correct inequality. And you can put 0.01 there. So that's 2.58.
So you have to subtract 1 for the point for when it's a right-tailed test. Is that what it was? Because you get
the degrees of freedom is n minus 1 for all of them.
Sorry. Well, because you said like It's 0.01 and then you put in 0.99. Why did we?
Okay. So what happened when I was here? Well, it was this, let me clear all this out and so we can see. This inequality, I can tell it that it's a right tail test. So here, that tells it it's a right tail test. So I can just put in the significance level there. In the calculator, what I was trying to kind of tell you what the difference between it, you can't tell this it's a right tail test. The way that you tell it it's a right tail test is you put in 0.99 instead of 0.01. Does that make sense?
Kind of. So like, why is it 0.99? Like, will it all, like, yeah, why is it 0.99? Like, what did we have to do
It
to
is a
get?
right tail test. So if you remember the right tail test, it's this area right here. So all of this is 0.99. This is 0.99. So it's actually going out to this gate right here. That's what is you're telling the calculator, hey, I'm on the right side now.
Okay.
So basically because the calculator doesn't do right tail like specifically is what you're saying?
Right.
Okay. Yeah.
So we have
Okay.
to, does that make sense then now?
Yeah, and that part makes sense. So like, if it was another number, how would you? You see what I'm saying? Like, how would you calculate that? Like, if it wasn't 0.01, how would you calculate that? Like, if it was I don't know, like 0.02, would it still be 0.99? Like, how
It
would
would
you
be
get?
0.98.
Oh, 9. Okay.
So it's 1 minus the significance level.
Okay, that's what I was asking. Okay.
Oh, okay, cool.
Sorry, thank you.
No, I'm glad. We need the clarity. Yes, thank you, Monica. It's 1 minus 0.01. Yeah. Okay, awesome. Oh, okay. And now we got a two-tail test. So how do we do a two-tail test? We can use table 5 again. And we would look at, and this is the 10.10 level of significance. One critical value is negative and one is positive. So you can actually look up, let's go here. Goodness gracious. Okay, so with these, alpha is split between these two sides. So that means I have 0.05 here and 0.05 over here on this side. So when I put it in the calculator, I need to put in 0.05 and not 0.10 because it's a two-tail test. And here's a picture, which makes it a little bit better. And so now let's get to actually doing the hypothesis tests. So we're going to use a t-test for the mean mu when the population standard deviation is unknown. The standardized test statistic is going to be t equals x bar minus mu divided by s divided by the square root of n. Okay. So when we did z, it was the same kind of idea, but this time I had the population standard deviation divided by the square root of n. So that's the kind of the difference between the two. I'm using the population standard deviation on one and the sample standard deviation on the other one. And the conditions that need to be met, sample is random, the population is normally distributed, or n is greater than or equal to 30. And then again, the degrees of freedom is n minus 1. So let's put it all together in an example. We have a used car dealer says that the mean listing price of used vehicles sold in the last 12 months is at least $23,500. You suspect this claim is incorrect and find that a random sample of 14 used vehicles sold in the last 12 months has a mean price of $21,558 and a standard deviation of 3350. Is there enough evidence to reject the dealer's claim at alpha equals 0.05? Assume the population is normally distributed. Well, the first thing we need to do is look at what the claim is. We're going to select the dealer's claim this time. And so, like the example we had at the very beginning, our claim, we were checking our claim. We thought it was incorrect, and we were checking our claim. This time, we're checking the dealer's claim. So that means the null hypothesis is going to be the claim in this case. So very important to identify what the claim is, because that way we can look at our decision matrix and see. So is at least 23,500 is at least 23,500. So that's greater than or equal to. And the alternative hypothesis is the opposite of that. So it's less than 23,500. And this is our claim. So we'll check that out. We're going to calculate our T. Remember, it's X bar minus the population mean divided by S divided by the square root of N. So X bar is 21,558 minus 23,500 all over sample standard deviation was 3350 over the square root of N was 14. So let's find what that T value is. Oh, I'm in the way. $21,558 minus 23,500 divided by 3350 divided by square root of 14. Negative 2.17. And notice this is a left tail test. Okay, so what is our critical value? What is our critical value? How do we find it? We can use the table or we can use our calculator. Walk me through the steps from here. How do we find our T critical value? StatCrunch. Let's go to that one. We're in the calculator. Left tail test. That calculator's T. Okay. Degrees of freedom, 13. And what was the level of significance? 0.05? 0.05. So negative 1.77. Make sure I have my degrees of freedom correct. Negative 1.77. So what does this look like? I'm gonna put a better graph on screen. But I didn't want to reveal the answer just yet. So let's draw the picture here. Oh, back. I want to draw the picture. What does it look like? This is a left tail test. Our T statistic is negative 2.17. Wow. Doesn't want me to be great today. So here's our T critical value, negative 1.77. Our T statistic is in the rejection region. Negative 2.17 is inside the rejection region. So that means what? The claim was the null hypothesis. We look at our graphic that you have somewhere close, right? The claim was the null hypothesis, and I am in the rejection region, so I'm rejecting the null hypothesis. And so there is enough evidence to reject the claim. And what is the claim? That the mean listing price of used vehicles sold in the last 12 months is at least $23,500. So we kind of went from top to bottom with that one. There is enough evidence to reject the claim. All right. So in the TI 84 calculator, we're on t-test now. So stat, tests, and this time you're on t-test. Let's get our information from the problem, 23,500. X bar was 21,558. The sample standard deviation, that is 3350. N was 14. And we have our, and we're at the alpha equals 0.05 level. We've got our T statistic of negative 2.17. And I've got the wrong test, don't I? This is supposed to be a left tail test. Oh, I didn't show you. Here we go. Down here at the bottom, I can select this is two-tailed, left tail, right tail. I'm looking for the left tail test in my software, my TI-84. And so notice the p-value is less than 0.05. So that also tells us we're going to reject the null hypothesis, along with what we did here with our graph to tell us where the rejection region is. And we talked about that last week. So there is, what was it? H sub 0 is the claim, and we're rejecting. So there is enough evidence to reject. Okay. Now for StatCrunch, we're going to go stat, calculators, not calculators, stat, t-stats, one sample with summary. Notice I'm in the same place that I go to calculate the confidence interval. So just kind of keep that in mind. The confidence interval and hypothesis testing are together in the same spot. So if you know where one is, you know where the other is. So the sample mean was 21,558. Sample standard deviation was 3350. Sample size was 14. A hypothesis test, 23,500. And this is going to be a less than. Let's show the critical value. And here's my test. So I've got my t-statistic is going to be to the left of the critical t-value. And my p-value is less than 0.05, so I will reject the null hypothesis. Those are the two ways that you can work the technology to conduct a hypothesis test. And so what we'll do on the next one is we'll look at the by hand, and then we will calculate with technology. All right. An industrial company claimed that the mean pH level of water in a nearby river is 6.8. You randomly select 39 water samples and measure the pH of each. The sample mean and standard deviation are 6.7 and 0.35 respectively. Is there enough evidence to reject the company's claim at alpha equals 0.05? Okay. So is this a left-tailed, right-tailed, or two-tailed test? Is this a left-tailed, right-tailed, or two-tailed test?
Two-tail? Two-tail?
Yes, you are correct. It is a two-tailed test. So mu is equal to 6.8. And the alternative hypothesis is not equal to 6.8. We have our X bar, we have our sample standard deviation, and then we have our sample water in of 39. Okay, let's calculate our t-statistic. Remember, that's X bar minus the population mean divided by S divided by the square root of N. So X bar is 6.7 minus 6.8 all over 0.35 divided by the square root of 39. Let's grab our handy dandy calculator. Negative 1.78. Now this is a two-tailed test. So how do we, or how do you want to find the critical value?
I think first you got to divide the alpha by 2.
Okay,
And then
so
put that in the calculator.
okay. Let's go here. 0.05. So 0.025 verse T. What goes here? Ooh, what goes here? Let me uncover it so you can see. In our calculators. Stumper. And it's weird, and in the calculator where it tells you what to put, it has a V, but it really stands for degrees of freedom. So Let's put our degrees of freedom in there. And negative 2.02. And if we draw our graph, since this is a two-tailed test, I'm taking the positive and the negative. So where does our test statistic fall?
What do you mean? You said where does it fall?
On our graph. Where is it located? Where would you situate this negative 1.78? Is it in a rejection region or is it in a non-rejection region?
The rejection region?
So anything that's going to be rejected is going to be less than negative 2.02 or greater than 2.02.
Oh, the non-rejection.
Right, so this is going to be a non-rejection region. So negative 1.78 is somewhere in here, so I failed to reject. What was the claim? This was the claim. Okay, so what is our wording here? Okay, so Avery says there is not enough evidence to reject. So I'm at H sub 0. I failed to reject. So yep, there is not enough evidence to reject the null hypothesis. There's not enough evidence to reject the null hypothesis. That the mean pH level of the water in a nearby river is 6.8. So we did that from top to bottom. And now, since we have our technology, let's go ahead and use it. And hypothesis testing, stat tests, and we're on t-tests. This time, we're at a two-tailed test, and mu was 6.8. 6.7 is my sample mean. Sample standard deviation is 0.35, and n was 39. And notice my p-value is 0.0. Oh, I'm sorry. I was doing all that typing and you didn't even see it. Rewind. I was up here, selected the two-tailed test, and then 6.8, 6.7. I'm just putting in the information, 39, hit enter. And notice my p-value is 0.082. Well, my p-value 0.082 is greater than my significance level of 0.05. So this also tells me that I failed to reject. So you can use rejection regions, or you can use a p-value to reject or fail to reject. All right, any questions on that? Okay. So you know what tail it is from the alternative hypothesis? The question was, how do you know which tail it is again? So if it's not equal to, it's going to be a two-tailed test. If the alternative hypothesis has a less than symbol, this is a left tail test. And if the alternative hypothesis has a greater than symbol, that's going to be a right tail test. So basically, I tell myself wherever the null hypothesis is pointing, like the left tail is pointing to the left, the right tail is pointing to the right, and then wherever the alternative hypothesis is pointing, left, right. And then the not equal to, it's not pointing in either direction, so it's both. Okay, cool. Let's do one more example here, and then we'll pop into proportions. Right. Department of Motor Vehicles Office claims that the mean wait time is less than 14 minutes. We got a random sample of 10 people, got a mean wait time of 13 minutes, standard deviation of 3.5, and we're testing at alpha equals 0.10. So which one is my claim? The null hypothesis or the alternative hypothesis?
The claim is the alternative.
That is correct, because they said less than 14 minutes. Claims that the mean wait time is less than 14 minutes. So that means the opposite for the null hypothesis. We'll get our test statistic. Y'all are going to be about sick of this test statistic. Like, she did this example 10 times. Good. That way, you'll remember come test time what to do. So I'm just filling in information. X minus mu divided by standard deviation of the samples divided by the square root of n. I've got 13 minus 14 over 3.5 divided by the square root of 10. I'm just going to grab this handy dandy calculator. And I didn't need to put that in there. So negative 0.903. And we have a left tail test. So we can go to, we haven't been doing a lot of StatCrunch tonight. That calculator's T. We've got a left tail test and the area is 0.10, but the degrees of freedom is 9. It's negative 1.38 as our T critical value. So we draw our graph. The rejection region starts here at negative 1.38. What is our decision? What is our decision going to be? Then the rejection region, right? So negative 0.903 is somewhere there. So we're failing to reject. And the claim was the alternative. So what is the wording that we use? And every time you should be referring back to your graphic Claim was the alternative. So we're in column 2. And we failed to reject. So we're in this bottom row. Yep, so there is not enough evidence to support. Not enough evidence to support the claim. It's okay. And you know how to do this by hand for the most part. Again, the only thing that when we use this method of drawing the graph and checking the rejection region, and we haven't calculated the p-value of negative 0.903, but we could do that with technology. But let's do StatCrunch to check out our solution. Stat T-stat, one sample with summary. Oh, one sample with summary. Sample mean was 13. Sample standard deviation 3.5. Sample size was 10 and 14, and this was less than. Show our critical value and compute. Ooh, look at that p-value. 0.1949. That is definitely greater than 0.10. So that's another way we can tell that we're going to fail to reject the null hypothesis. And there is not enough evidence at the 10% level of significance to support the office's claim that the mean wait time is less than 14 minutes. Any questions on that? Confidence intervals now for population proportion. So on this section, there's going to be, it's like a couple more formulas that we have to use. So let's pop one in here. All right. Population proportion P. Probability of success in a single trial of a binomial experiment is P. The point estimate for P, the population proportion of successes, is given by the proportion of successes in a sample and is denoted by P hat is how we say this. P hat equals X over N, where X is the number of successes in the sample and N is the sample size. We're going to need to know what Q hat is, and that is just 1 minus P. Q hat is 1 minus P hat. All right. So in a survey of 540 US adults, 378 say that they plan on traveling this summer. Find a point estimate for the population proportion of US adults who plan on traveling this summer. Well, let's look at our formula. Population proportion, a point estimate, excuse me, of X over N. Well, X they gave us is 378, and then we're going to divide that by 540. That's our point estimate. What percentage is that, by the way? Anybody have their handy dandy calculator out? 0.7. Thank you, Monica. So that is 0.7. Or 70%, right? Okay. Now, to build a confidence interval for the population proportion, we're looking a little bit different now. The margin of error is looking a little bit different than what we worked with before, right? So the margin of error is equal to Z critical times the square root of p hat times q hat divided by n. And remember Q is just 1 minus p. So the probability of the confidence interval contains p is C, assuming that the estimation process is repeated a large number of times. And this is a C confidence interval for the population P, proportion P. Okay. All right. Use the data in example 1 to construct a 95% confidence interval for the population proportion of US adults who plan on traveling this summer. And we calculated the population proportion to be 0.7. So P hat was equal to 0.7. So that means Q hat is equal to 1 minus 0.7, which is 0.3. And then our margin of error is equal to Z critical times square root of P hat times Q hat over N. Okay. So who remembers how we find the Z critical value? We could look at a table. And one thing that you can keep close to you is a common Z critical values. Find one here. Notice here, this is something you might want to keep on your note card. At the 95% level is 1.96. And the way we found that was we looked up 0.95 backwards lookup in our table to find that critical value. And we use the between calculator in StatCrunch. So we have a common value of 1.96 for 95%. And so we have 0.7 times 0.3 all over, I believe it was 540, but let me look back at, let's look back at that other page. Yeah, N was equal to 540. And so now, let's throw this in our handy dandy calculator. Uh-oh. Let me make sure my AirPlay is on. It turned off on me. I didn't think it had been that long. So 1.96 times the square root of 0.7 times 0.3 divided by 540. I wonder if I need to no, I think that's right. As if it follows our order of operations is what I was thinking about. So 0.039. Stuff on screen. And so now my proportion my confidence interval is going to be proportion P 0.7 minus 0.039 is less than the proport. Oh, I meant to put proportion here. I meant to put the actual number. Okay, so we have 0.661 less than P is less than 0.7 plus 0.039, 0.739. So that is my confidence interval. And so what does that mean? With 95% confidence, you can say that the population proportion of US adults who plan on traveling this summer is between 66.1 and 73.9%. So let's go back and put that into the calculator. And one thing that I did miss here, when we're constructing a confidence interval, there's one thing we need to check, and that's this, that n times p hat is greater than or equal to 5, and n times q hat is greater than or equal to 5. They're going to ask you that on the homework, and I totally forgot about it. But we have to check that condition. And that's just seeing if we can approximate it with a normal distribution. So let me make sure I get to my screen where I can see. I wrote myself some instructions somewhere, but we're gonna wing it. We're looking for a 95% confidence interval is what they told us. Yeah. All right. Stat tests and where is, there we go. One is A. It's all the way down here at the bottom. It says 1 prop Z int. So it's this one. And X is going to be 378. N is 540. Confidence level is 0.95. So that's how we do it on the TI calculator. And now to move to StatCrunch. It's very intuitive as well. So stat, proportion stats, one sample with summary, number of successes, 378, number of observations, 540. Confidence interval for P at the 0.95 level. I just leave standard wall there and compute. And you get the same thing. 0.6612 to 0.739 as the confidence interval. Okay. Okay. Let's try another one. Okay. All right, this figure below is from a survey of 800 US adults. Construct a 99% confidence interval for the population proportion of US adults who prefer to get their news from television. So just going back, prefer to get their news from television. We're right here at the 35%. Prefer to get their news from television. And let's check our conditions in P hat has to be greater than or equal to 5, and N times Q hat has to be greater than or equal to 5 as well. So we're going to multiply 0.35 times N, which is 800. And we're going to multiply 0.65 times N, which is 800. And we're checking to see if it's greater than or equal to 5. But what is this number? What are those numbers? 0.35 times 800 and 0.65 times 800. I'll let you calculate them. I've pulled out my handy dandy calculator enough. I'll let you guys pull out your handy dandy calculators. What are those numbers? All right, 280 and 520. So we pass. We can approximate this distribution with the normal Z critical value, and this was 520. Okay. Now we need to do some more calculations. Let me see if there's some more room on this next page. Okay. This says using a Z critical of 2.575. Remember, you want to have like some common codes here. 2.58 is 99%. That's where the 2.575 comes from. Again, you can use the inverse normal calculator, inverse normal, or you can use StatCrunch with the backward lookup. Okay, so what I've done here is I'm multiplying 0.35 times 0.65 all over 800 and getting 0.043. So in order to find my left and right, he had minus E. It's approximately 0.35 minus 0.043. And then P hat plus E is going to be, I'm going to approximate 0.35 plus 0.043. Now I'll just tell you those numbers are 0.307 and it's less than P. Is less than 0.393. So we can be 90, was it 99? 99% confident that, what was the problem situation? I forgot. The true mean for US adults preferring to get their news from television is between, go back to our screen, 30.7 and 39.3%. And I just turned those into percentages. All right. The last thing we're going to do in this section is find a minimum sample size. So in that, you're just applying the formula. We worked backwards to find N in this case. So P hat, Q hat times Z critical over the margin of error squared, the quantity squared. If N is not a whole number, then round N up to the next whole number. All right, the formula assumes you have an estimate for P and Q. If you don't have an estimate for P and Q, use 0.5 and 0.5 respectively. Okay. You're running a political campaign and wish to estimate with 95% confidence the proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the true population. So we don't have a preliminary estimate, so we're going to use 0.5 and 0.5. And I know we're just about at break time, so I'm going to finish out this example and we'll head on to our 10-minute break. Z critical is 1.96. They told us 95% confidence level. E is 0.03. Notice they were 3% and they went to 0.03. And I just plug it into my calculator, into the formula, and I get 1,067. Look, I'm all right. My brain is on break. So here's the last part of that. With no preliminary estimate, the minimum sample size should be at least 1,068 voters. You're running a political campaign and wish to estimate with 95% confidence the proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3% of the true population. So we need to find out what Q hat is, right? What is Q hat going to be? If P hat is 0.31, what is Q hat? Right, 0.69. This is 1 minus P hat. So it's 1 minus 0.31, so 0.69. So N equals, let me get back to the formula here. To write the formula here. P hat, Q hat times, oh, not the square root, Z critical all over the standard error. That looks just all messed up. I'm gonna fix that. E critical over the standard error squared. So 0.31 times 0.69 times 1.96. That's the one of our common critical values over 0.03 squared. And what do you get when you put those together? Do the math on that. What do you get when you multiply?
913 point, I guess you round up to 0.02. 913.02.
And so we're going to round up to 914 because we're talking about people, and that is discrete. So the minimum sample size we need is 914 voters. Hypothesis testing for proportions now. All right. A Z-test for a population proportion. Okay, so basically we're doing the same testing we've been doing, except this time it's on the population proportion. We're still gonna verify that NP is greater than or equal to 5 and NQ is greater than or equal to 5. The test statistic is the sample proportion P hat. And the standardized test statistic is Z. And so P hat minus P, the proportion, over P times Q divided by N. That's our Z value. So in words, we'll verify that we can use the normal distribution by the NP and NQ being greater than or equal to 5. Again, we'll state the claim, the null alternative hypothesis, and state the claim. We will identify our level of significance, determine the critical values, and we have a couple of methods for doing that. You definitely look at the table, or you can look at the common critical values. That would be helpful here in this case, and or use the calculator or StatCrunch. Determine the rejection region, and then make a decision whether we fail or reject. Fail to reject or reject the null hypothesis. All right, let's do it. A researcher claims that less than 69% of US adults who use live television streaming platforms have upgraded to advertisement-free service tiers. Okay, it's a mouthful. We've got a random sample of 100 US adults, 65% say they have upgraded to advertisement-free service tiers. Oh, okay. So basically it's something like when you subscribe to YouTube TV and you paid to watch YouTube ad-free. Okay, I see what they mean. At alpha equals 0.09, is there enough evidence to support the researcher's claim? Well, let's first check NP times NP greater than or equal to 5. Remember, NP greater than or equal to 5 and NQ greater than or equal to 5. So N is 100 and P is 0.69. What's this P hat? Yeah, 0.69. And is that greater than or equal to 5? And then 100 times 0.31, is that greater than or equal to 5? Well, we got 69, nice numbers here, right? 69 and 31, so that checks out. So we can use the z-tests. All right. And then the claim is less than 69% of US adults who use live television streaming platforms have upgraded. So the null and alternative hypotheses are listed here. And the Z critical value for alpha equals 0.01, so negative 2.33. That is what we're going to use for the rejection region to define the rejection region. And we need to calculate the standardized test statistic. So that's 0.65 minus 0.69. And then we've got 0.69 times 0.31 divided by 100, which is approximately negative 0.86. So now, when we draw our graph, since I've got so much room here, I got negative 2.33. And our test statistic is negative 0.86. So negative 0.86 is somewhere over here. Are we going to reject or fail to reject the null hypothesis? And let me write the claim here. Why does my pen keep going away? Okay. Fail to reject. You are correct. We are going to fail to reject the null hypothesis. So the claim was, which one was the claim? The alternative. All right. So we're failing to reject, and we're going to see what that means with our handy dandy graphic. The claim was the alternative. We're failing to reject. So our wording is not enough evidence to support the claim. There is not enough evidence to support the claim. And when I say the claim, you would fill in whatever information came from the problem. Okay. All right. Okay, we got a researcher that claims 26% of US adults ages 22 to 59 who do not have a parent with a bachelor's degree have completed a bachelor's degree themselves. Okay. In a random sample of 7,400 adults who do not have a parent with a bachelor's degree, 1984 say they have completed a bachelor's degree themselves. At alpha equals 0.10, is there enough evidence to support the researcher's claim? Well, the first thing we're going to do is test out our NP, right? Okay. NP is greater than 5, and NQ is also greater than 5. So then we're going to move forward with the z-test. The claim is 26% of US adults ages 22 to 59 who do not have a bachelor's parent with a bachelor's degree have completed a bachelor's degree themselves. So the null and alternative hypothesis given here. Okay. This is a two-tailed test. Level of significance is 0.10. We got our critical values as negative 1.645 and 1.645. So our rejection regions are on either side. Of our drawing. Here's a drawing. Oh, the drawing's not there. We got our test statistic at 1.59 and our rejection regions. (1.645). And negative 1.645. So our standardized test statistic, where is that falling at? Are we going to reject or fail to reject this one? You are correct. We failed to reject. All right, and so we got to look back. Which one was the claim? It was the null hypothesis. Yeah, it was the null hypothesis. So with the null hypothesis being the claim and we failed to reject, null hypothesis being the claim and we failed to reject, there is not enough evidence to reject the claim. There's not enough evidence to reject the claim. Is this going to tell us that? Yep. So have we gone through this whole section and done no technology? You will have to check the NP yourself. Let's go back to this one. And let's look at, again, we'll start with StatCrunch this time. Proportion stat, one sample with summary. Now, how did I determine the number of successes? Well, what I did was, let's go look at the problem itself. So right here, we have 65% of 100. So that is 65 out of 100. I just multiplied 0.65 times 100. And then 100 was the number of observations. And then my test, of course, you know what you fill in here. And then I did the show critical value. Make sure your alpha level is correct. And then your Z statistics are there. And we failed to reject. Our p-value is greater than 0.05. So of course, that's another way we know that we're going to fail to reject the null hypothesis. Okay. Let's do this in the calculator. And stat tests and one proportion Z test, that's number 5. This was a less than, my P of 0 was 0.69. There we go. I made sure at the bottom that I selected the less than. And then put in the specifications of the problem. The P0 is the population or the claim amount, the 69%. And this is a left tail test. Gives you the Z statistic and the p-value and p-hat. So let's look at that last example in technology. We are done. Okay. So what is going to be my X and what is my N? If I were going to figure out, because each of the technologies you have to enter in your p-hat. And in this case, oh, they gave it to us. We have 1984 over 7,400. They gave it to us that time. So let's go back and look at our result here. And we'll look at it in technology. We'll start with the calculator. And this was I believe it was a two-tailed test, correct? Yes. So I'll select the two-tailed test. I'm going to go back and adjust my specs. 26%, 0.26. And it was 1984 out of 7,400. Is that right? 0.26. Z was 1.59, P is 0.111. That tells us this P of 0.111 tells us we're failing to reject because at the, what level was it? 0.10, that's greater than 0.10, the 0.11. So we failed to reject in that case, which is the solution that we came up with before. Let's look at StatCrunch. I'm just going to edit the one that I have here. 1984, 7400, 0.26. It was a two-tail test. And I was at 0.10. The Z statistic is 1.59. We're comparing to 1.645, and the p-value is 0.118. So everything that we've done today can be done in the calculator. But I think it's important for you to have the inner workings of it to know what we're putting in the calculator and why we're putting it in the calculator. Anywho, any questions on that? Any questions on hypothesis testing for proportion?